All right, I'm here with Maria Violaris. Maria, thanks for joining me.
Thanks for inviting me.
Sure thing. So before we get into your research, let's do a little background physics. So what does it mean that the dynamical laws of physics are time reversible? And specifically, what does this mean in the context of quantum physics?
Yeah, so the dynamical laws of physics being reversible is something that we see not just with quantum physics, but also with normal classical physics, with classical mechanics and electromagnetism. There's this property that when we look at the dynamical laws, they don't distinguish between a process happening forward in time and a process happening backwards in time. So if we look at any system around us and we zoom into what's happening to the particles, and then if you played a video of them interacting forwards in time and then you reversed it to happen backwards in time, the dynamical laws let us allow those interactions to happen both ways in time. So when we say that the dynamical laws are reversible, we mean that when we look at the laws of physics that we're using to describe how systems are interacting, we can reverse them, and the laws of physics are completely fine with that. The dynamical laws are fine with that. So the way that happens in quantum theory specifically is that when any interaction that's allowed within quantum theory, the reverse interaction is also allowed within quantum theory. So any process that happens that we use quantum mechanics to describe it and we use our quantum equations to describe it, then we can also use these equations to describe the reverse process happening. So that's how we see this. This reversibility is a property inherent in the laws of quantum mechanics.
So even though quantum mechanics is time reversible, as you just explained, it still, from my understanding, gives rise to irreversible processes on the macro scale. So could you please explain, maybe with an example, what this means in the context of quantum mechanics?
We see lots of irreversible phenomena on large scales, like just in daily life, we see lots of irreversible phenomena. As an example, like an egg being scrambled from being a yolk and a white to being mixed up into a whisked egg where the yolk and the white are mixed together. We can go from a yolk and a white to a mixed egg, but we can't go from a mixed egg to the yolk and white again. So that's an example of something that's irreversible on our scale. But if we zoom in to try and describe the particles of that egg using quantum mechanics to describe how the molecules are interacting, then each of those interactions would be reversible on that scale if we zoom right into the scale where you're describing things using quantum mechanics. So the problem is that we trying to describe irreversibility on the scale of the large things, there isn't really a way of framing that using quantum mechanics other than kind of starting from the quantum mechanics scale and then trying to make approximations and assumptions to try and get to this thing that we see as our macroscopic irreversibility on the large scale.
So is it fair to say that by only looking at time symmetric equations of motion, such as those we find in quantum mechanics, you would never be able to explain the emergent level irreversible phenomena that we see? You would need some other way of explaining reality?
Yeah, so there are it's a very current topic of research trying to derive this, trying to see if we can get this kind of irreversibility out of quantum mechanics. And sometimes you have to make these assumptions about having a large system or making approximations, and you end up with kind of probabilistic laws saying that things are probably irreversible, but we can't make kind of exact statements about that. And there's various attempts to kind of derive irreversibility by making different assumptions about the specific quantum system that you're looking at. But it's quite a kind of, there isn't a really fixed way that everyone's agreed on understanding how irreversibility can come out of the reversible laws. It's more like looking at specific scenarios on a case-by-case basis and seeing how can we reconcile the irreversibility we see with the reversible dynamics of this quantum system.
So is it fair to say that in the what's called the prevailing conception of physics, namely explaining the world through initial conditions and laws of motion, there hasn't been a satisfactory solution to the problem of how you have macroscopic irreversibility along with time reversible dynamical laws of motion? Is that fair?
Yeah, that's right. Yeah, there's lots of different ideas, different approximations and assumptions, and it's a very debatable topic of exactly what happens on the quantum scale with irreversibility.
And from a practical perspective, why is this an important problem to solve, this reconciling macroscopic irreversibility with lower level time symmetric laws of motion?
Yes, I think practically it's a really interesting problem that we need to solve because as quantum technology is improving really rapidly at the moment, and we're kind of getting to the position where we're starting to be able to manipulate quantum systems and use experiments to actually see what's happening on the scale, which we couldn't do in the past. So, and as we improve our technological capabilities at that scale, to be able to try and turn that into practical technologies, we really need to understand how irreversibility works on the scale. What are the fundamental limits of what we can do with quantum mechanics, and can we reverse things on a quantum scale? Does that mean that there's a type of technology that we can create that can perform some kind of reversal, or is there processes that are fundamentally that we fundamentally can't do within the laws of physics? So without knowing what the rules of thermodynamics and irreversibility are on the quantum scale, then we don't know what the limits are of our technology on that scale, and what kinds of and what the potential is of our technology as we keep improving it and try and find practical uses for it.
So in other words, the approximation schemes that you said people were trying to do here and there in reconciling irreversibility with underlying time reversal laws, we could maybe get away with using approximation schemes at large enough scales, but the rubber really meets the road when we're trying to create technologies at the nanoscale, at the quantum scale. We really need to understand in principle how time irreversibility can possibly be reconciled with, let's say, the laws of quantum physics. Is that right?
Yeah, that's right. I think for being able to design new systems and technology that's using quantum mechanics, then we need to really understand all these laws at that scale, just like normal thermodynamics was really important for creating engines on our scale, and that we've seen in the past in history for technological development.
Right, very interesting. So constructor theory, which is something you've been working on, is a new mode of explanation in physics that seeks to express all of the laws of physics in terms of possible and impossible transformations, rather than the prevailing conception that we've already touched on. So how might constructor theory, rather than the prevailing conception, help us to bridge the gap between time reversible dynamics and macroscopic irreversibility?
So the interesting thing about constructor theory is that one of the interesting things about constructor theory is that you can frame irreversibility in a different way to how we view it when we think about dynamical laws. So in the kind of prevailing conception, we take some initial conditions and we have the dynamical laws that we know describe how that system is going to evolve, and then we see how it evolves and try and draw conclusions about how it will evolve using those dynamical laws. And with constructor theory, we take a different approach where we look at, are you allowed to transform some state to some other state? And we consider, if you want to transform some state to another state, then, and you want that to be the only thing that happens, then whatever performs that transformation has to remain unchanged. because if it's changed, then you've done something other than just transforming A to B. If you've transformed A to B with other things happening, then that's not the only thing you've done. So that's what you call a constructor, is the thing that performs this transformation without being changed itself. So the way that this allows you to kind of reframe irreversibility is that you can have a constructor, so something that performs a transformation without being changed to transform something from a state A to a state B. But it might be the case that there isn't such a constructor to transform the state B back to the state A, even if the individual interactions by which the state A turned to the state B in the first place are reversible in themselves. So you can say that performing one transformation is possible and transforming the inverse transformation is not possible, even when the underlying dynamics by which that transformation happened were reversible, the dynamical laws. So by looking at these transformations of states from one state to another and whether they're possible or not, you get this different way of making exact statements about irreversibility, because we're not saying that this happens on a certain scale, we're just saying this task is possible, A to B, but B to A is not possible.
Yeah, so you touched on something I was going to follow up about, which is it sounds like constructor theory offers an exact way to characterize irreversibility in a given domain, rather than the approximation schemes that have been applied in previous attempts to explain the regularities that we see in terms of irreversibility.
Mm-hmm. Yeah, that's right. So you can say exactly that transforming the state A to state B is possible and transforming B to state A is not possible, without having to say this only happens when you have a system with a large number of particles, or this only happens when you assume that you're interacting in a certain way. So it allows you to make more general statements about the irreversibility of a task, rather than tying yourself to some kind of undefined scale, which leaves things quite ambiguous, and that's how a lot of explanations of irreversibility are at the moment.
So you've been working on a toy quantum mechanical model called a quantum homogenizer as a kind of test case to demonstrate how reversible dynamics give rise to higher level irreversibility. So first of all, what is a quantum homogenizer, and how exactly does it serve as a test case example of what we're talking about?
Yeah, so the homogenizer is it's basically a machine made of qubits. So the qubit is a quantum bit, which is a generalization of the bit that we're familiar with in from classical computing, where a bit can be a 0 or 1, and qubit can be in a 0 state, a 1 state, or a combination of 0 and 1. So the quantum homogenizer is made of lots of these qubits, and the idea is that you have a reservoir of lots of identical qubits. So they all begin in the same state, and that can be any state as long as they're all identical. And then you have a system qubit, and this can begin in any other state, and this is the qubit that we're going to homogenize. And then your system qubit interacts with your reservoir qubit, so this set of identical qubits, it interacts with one of them. And the way it interacts is via this quantum interaction, which we call a partial swap, which kind of swaps the states a bit. So the system qubit becomes a bit more like the homogenizer qubit, and the homogenizer qubit becomes a bit more like the system qubit. And so then you do the partial swap with all the other homogenizer qubits. And after having done an interaction between your system qubit and all these homogenizer qubits, then your system qubit ends up in the homogenizer qubit state, because it's been getting closer and closer to the homogenizer qubit state from all these partial swaps. But the homogenizer qubits have stayed very similar to the state that they were in before, because each of them has only done one partial swap with the system qubit. So if you do really weak partial swaps, so that each one of them isn't changing the homogenizer qubits very much, but you do it with loads of homogenizer qubits, so that your system qubit will become really close to the homogenizer state, then you can have a machine that turns the system qubit from one state to another and homogenizes it to the homogenizer state. But the homogenizer stays almost the same as it was before. So this is why, so now you can see how we're going to get the link to constructor theory, because the homogenizer is a machine that can perform a task while remaining, well, it seems like it can remain unchanged, almost unchanged by performing the task. So it's a kind of candidate machine for a constructor for the task of transforming a qubit from one state to the state of the homogenizer qubits. So that's the kind of the context of how the homogenizer works and how you can have how it can behave potentially as a constructor. So the way that it links to irreversibility is when you compare two specific tasks that the homogenizer can do. So one of them is transforming a qubit from a pure state to a mixed state, and another is transforming it from a mixed state to a pure state. So pure states and mixed states are kind of different types of states that the qubit can be in, and what I found is that when you try and use the homogenizer to transform a pure state to a mixed state over and over again, then it's possible to do that transformation to any accuracy you want, any number of times you want. But if you try to use the homogenizer to transform a mixed state to a pure state over and over again, then the homogenizer deteriorates too quickly to use it to use it as many times as you want because of its interactions with the qubit it's been trying to homogenize. And so the homogenizer is a constructor for the pure to mixed transformation, but not for the mixed to pure transformation. So this is how we get one task being possible, which is mixed to pure. Which is pure to mixed is possible, whereas mixed to pure is not possible using the quantum homogenizer, even though all the interactions that the homogenizer did with the qubits, they're all completely reversible, and they're just completely within quantum theory using reversible quantum dynamics. So that's how we get this irreversible, constructor-based irreversibility coming out, even with reversible dynamics in the homogenizer.
And could you please quickly define the difference between mixed states to pure states? I understand in this context, it might not be necessary to even know the difference, only that they are different, but I wonder if you could clarify what the differences are, please.
Yeah, so a pure state, if you know the pure state that the qubit is in, then if you try and then if you tried to measure that qubit, you always know exactly which state it's in. So whereas with a mixed state, if it's fully mixed, then if you try and measure which state the qubit is in, however much information you know about the qubit state, you've got an equal chance of getting a 1 or a 0. So a mixed state has this kind of inherent randomness when you measure it. You don't know which state you're going to get. Whereas with a pure state, if you know that it's in a pure state, then there is some way that you could measure it and get an exact result where you know exactly if it's 1 or 0. So a mixed state has this kind of randomness property, whereas the pure state is the pure state you could measure exactly in principle.
So it sounds like you've shown that with the quantum homogenizer, if you take a pure state qubit, you can homogenize it using the quantum homogenizer to a mixed state an arbitrary number of times over and over with new qubits. Is that correct? With new pure state qubits?
Yeah, that's right.
But then the reverse is not true. If you take a mixed state qubit, you can't convert it using the quantum homogenizer to a pure state an arbitrary number of times. Is that right?
Yeah, that's correct.
So
yeah.
As you were saying, this directly translates to the constructor theory way of thinking about irreversibility, where we have state A can be transformed to state B. That's possible, but state B cannot be transformed to state A. That's an impossible task or impossible transformation.
Yeah, so in this case, because it's not possible to transform the pure state to the mixed state to a pure state using the homogenizer, that shows that it's not necessarily possible to transform a mixed state to a pure state using a constructor. But because we don't know if there are other systems that could perform the task, so we can't say conclusively that it's an impossible task. But what it does show is that transforming a mixed state to a pure state is not necessarily possible, even if transforming a pure state to a mixed is. So that's the kind of, so it might still be a possible task by some other machinery mechanism that we don't know, but the fact that this model shows that it can be the case that there is a possible task and a reverse task isn't possible. That's the kind of interesting conclusion that we can get from looking at the homogenizer.
And was there a particular metric that you used in your analysis of showing that one of these transformations is possible and the other might be impossible?
Yeah, so the metric that I was using was it was the relative deterioration. So the idea of this metric is that it takes into account two effects. So one effect is that if you make your homogenizer bigger and bigger, then it's going to become better and better at performing the homogenization, because you're going to get your system qubit to become really close to your homogenizer qubits. So you're going to perform the task really well. And the other effect is that if you use the homogenizer lots of times, then the homogenizer is going to deteriorate, because each time all its qubits interact with your system qubit, they get a bit further from their original states, and so they'll be less good at the next homogenization. And so the homogenizer gets worse every time it's reused. And so the relative deterioration takes into account the that when you increase your number of qubits, you get higher accuracy, but when you increase the number of times you've used your homogenizer, then you get a lower ability to perform the task. And what happens is when you take your number of qubits to be really large and the number of times you've used your homogenizer to be really large, then for the pure to mixed case, your relative deterioration goes low, because the accuracy you gain from adding more qubits overpowers the deterioration. Whereas the mixed to pure case, the relative deterioration increases, and the deterioration from using your homogenizer lots of times overpowers the extra accuracy you get from increasing the size of your homogenizer. So these are the two effects that are taken into account by the relative deterioration, and they behave differently for the forwards task and the backwards task of pure to mixed and mixed to pure.